It's a pleasure to be here. I don't know how many of you remember we started these seminars in 2013 or 12 with Sagi Cohen, long time ago. I joined the university, and for some time we didn't have seminars, and we were missing getting together and talking about water research. And now we are back together thanks to Zach, so thank you for continuing the tradition. So for those people who don't know me, my name is Natasha Dimova, and I am associate professor in the geology department. And my research focuses on coastal groundwater dynamics. But as you can see from my first slide, our lab is also considered as environmental radioactivity measurement lab, which means that if you have any issues with radioactivity and find something strange, you can bring it to our lab and we can tell you what is it. So with that, I'm gonna jump directly on the topic of the youth and the fountain of youth, as it triggered some discussion. So the myth about the fountain of youth actually originates in Florida, and it refers to the first Spaniards who explored Florida, who are looking for this fountain of youth. These are some pictures, showing Ponce de Leon looking for the spring that brings forever youth. This place is actually still there in Florida, in St. Augustine. I'm not sure if you know, but you can go and take a sip of the spring water and see what happens. The reality is that Florida has a lot of springs, and interestingly enough, some of them are on land, but some of them are pretty offshore in the ocean. And the photo that you see, black and white photo that you see on that side, right or left side of your screen, shows, depicts a picture of research crews they were drilling offshore of Florida, and accidentally they hit some water which sprayed as high as 5 meters above sea level. This was pure fresh water, and the fountain of youth in this case was 27 miles offshore of Jacksonville. So today I'm going to be talking about this type of water that we find near shore or even offshore. And just to confirm this and to bring you a little bit into the methods of how we evaluate this, which for hydrologists is called the lost fresh water in the ocean. I'm showing here two old maps produced in the 70s and 80s. And on one of the maps with the red dots, you see the locations of offshore springs, known offshore springs in Florida. And on the Floridan platform, as you can see, there are many of them. And then on the other side, what I'm showing here is the radon concentration or activities in water, in seawater, around the clusters of these springs. And if you can see the numbers on these contour maps, you will identify high levels of radon around the areas where we have identified these springs. So even in the 70s and 80s, people had discovered this connection between groundwater, spring water, and higher levels of radon in the waters where those springs are flowing. So pretty sure everybody had heard about radon. It's a naturally occurring radioactive gas. It exists in nature. It's a gas product of the decay of the parent radium-226. Radium-226 is part of the solid rock. So when it decays, or it just usually stays attached to solid phase. Whereas the radon, when it's produced, it diffuses through the porous media and saturates the pore water or groundwater. The result of it, we see areas of high levels of activities of radon, where we have seepages of this enriched water, enriched in radon water. So one would think that Florida is a peculiar place, but it's not, because there are springs around the globe, offshore springs pretty much everywhere. This is, at least to my knowledge, the last study a friend of mine did and published in 2017, where he identified knowledge or records of offshore springs that people know for a long time, and he tried to put them in different categories of what we are using this water for. And you can see some people are using the water for drinking, for irrigation, for other social purposes. It has also a lot of cultural meaning for the local communities. Typically, those communities are built around these sources of fresh water. So not unusual at all. All right? So if you want to follow the talk to the end, you have to learn the acronym SGD. Everybody who knows me knows the term, the acronym SGD. My students are smiling. But we have a specific term for the flow of groundwater to coastal areas, which we call submarine groundwater discharge. And this term was determined the first time in a paper, review paper by my advisor in Florida, Bill Burnett. And and very recently we published another review paper which sort of expanded the definition not only to marine systems, but also to freshwater systems. Because the same principle that we see in detecting offshore flow pertains for freshwater systems. We have developed methods that we can use radon as a prospecting tool to identify seepages in lakes and rivers as well. So by this definition, this is any type of water that has been in contact with the aquifer, with the rock, that enriches with radon or other radioisotopes before discharging into the receiving waters, regardless if it's a marine or freshwater environment. All right, so jumping onto why we are interested and what do we do with these facts or the research questions. This is a relatively new research field, though the first time, as I said, when the term was defined was in 2003, which is exactly 20 years. So it started with understanding what is the current state, where it discharges and how much of it. How does this water contributes to the nutrient and material budgets of the surface waters that experience this seepage? We also want to know more about what drives this water flow. So we want to know its variability, how it changes through times, what would enforce flow. And we want to be able to quantify this variability through time. Another thing that my group is particularly interested is how this groundwater flow and this specific subsurface water changes the chemical composition of and the transformation of those constituents that brings from land. Is the same water that groundwater we observe on land, is this water the same as the one that will discharge to the coastal zone? In other words, we are interested to see what are the changes of groundwater as it travels through the aquifer, through the coastal aquifers. And last but not least important, we want to see how people impact this source of water in short term, and now we have for 20 years a lot of data that we can start modeling long-term and large scale, because this would affect not only primary productivity near shore, but this is also exported new source of material fluxes to the global ocean. And this is very important because so far it hasn't been considered as a source. So there are several new publications where people started recalculating the residence time of major elements, silica, phosphorus, nitrogen, in the global ocean, including this new source. Okay. All right. So how do we do this? What methods we use to answer those questions? So I try to group those in 3 major groups. The large group that we use and we think we are experts in is the geochemical group of methods. We use not only radon as a tracer, but some other naturally occurring radioisotopes, such as the radium isotopes, as well as we use lead-210 to date sediments, calculate accumulation rates, and so forth and so on. We also use stable isotopes to identify the water sources and the sources of contaminations. For example, we've used N15 for tracing and identifying nitrate contaminations, as well as looking at organic matter characterizations to identify these sources. Very recently, we started a new avenue in our lab. I had a postdoc for 2 years who focused on identifying the microbial communities who mediate those biogeochemical changes in the coastal aquifers. In terms of larger scale characterization of these coastal aquifers, we use geophysical, shallow geophysical tools. We have electrical resistivity tomography. We use electrical resistivity to map the subsurface in this shallow coastal aquifers. There is one snapshot, which actually happened to be from a stream that up north in, it's a Bear Creek, but yeah, this is sort of the images we get when we take snapshots of the subsurface with the resistivity cable. We do a lot of sediment core collection because apparently the local sediments play a role when they interact with this flowing groundwater. And also, very, very new thing I was part of in collaboration with the group and one of my colleagues, Bo Zheng, who is a modeler. We did try to look at how we can use the large data of HGD we have accumulated through these 20 years in machine learning methods. The stage of this work is at the point where we are trying to, for example, use it for filling gaps when instrumentation hasn't been working to improve the overall estimates of HGD, but it's a very promising tool and I'm very impressed by this methods. So I'd like to talk to you maybe after that. All right, so the rest of my presentation, I'm gonna just go through these research questions and just show you some data that we collected. My examples are mostly from Mobile Bay, where we worked primarily in the last 6-7 years, but I would also refer to some global estimates on a paper that we published 2 years ago. Okay, so what forces the discharge? So we can look at this phenomenon at 2 scales. On a larger scale, which is this diagram here showing all the way 100 kilometers offshore and pretty much encapsulating the continental shelf. And the forces there are mostly marine forces, oceanic forces, which are a result of geothermal heating and overpressurized zone between different confining layers. But what our research group is focusing is the nearshore area, which is this small red box here that we zoom in. And again, this is the interface between land and ocean, so we would expect to have a combination between terrestrial and marine forces. And terrestrial forces, as listed here, of course, includes hydraulic head, buoyancy of fresh water. Fresh water is lighter than salt water, so that would play some role. And in terms of the marine forcing, it's a very common mechanism. One very common mechanism is tidal pumping. If you are down at the coast, you experience high and low tides. When we have high tides, simply explaining this forcing, when we have high tides, seawater intrudes the coastal aquifer, pushing further to land fresh groundwater. And when tide recedes out, it will release the pressure from the coastal aquifer, allowing for more fresh water to discharge. So when we monitor these 24 variations of SGD, we see clear tidal pattern into the discharge. So we are interested to understand how much, and through these tidal fluxes, tidal variations, what is happening in this interface between seawater intruding and fresh water coming from land. Okay, so often certain subsurface geometry, I would call it, could mediate or facilitate this flow. And this is a current project still. I'm working with some people in Mississippi where we hypothesize that paleochannels from rivers that have been now submerged could become conduits for freshwater, groundwater discharge to coastal areas. So what you see here is again Mobile Bay. This is from a paper that actually has been produced in my department some time ago. And the structures that you see here are those paleochannels where the rivers were flowing and the sea level was lower. And then when sea level rises, and you have those channels filling gradually with sediments, but those the sediment deposits have slightly higher hydraulic permeability, meaning that the water will flow easier through them, so they become naturally conduits for this offshore discharge that we see today. And I'm very happy to share this image with you. These are some of the first results. Adam Skarke from Mississippi State University and I made a couple of years ago already. This is showing you seismic data that he collected simultaneously with electrical resistivity data. This is our marine resistivity cable. You can put this cable to do snapshots in the subsurface, as I showed in my method slide. But you can actually deploy and drag behind the boat the cable, as it's shown in this photo. And you can start taking snapshot as we are driving shore parallel. And so when we were doing this simultaneously with the seismic data, with the seismic instrument, we were looking for these conduits. And what the seismic was able to figure out is the structure of those conduits. And you can see definite structure for these channels that I showed in the diagram. And the result from the resistivity is this one line here showing you the distribution of resistivity in these channels. And the red color means higher resistivity, which means lower conductivity, which means fresh water. So this is direct evidence from these two methods that those channels exist and they're full with fresh water. So they are conduits for discharge. And very similar thing we saw some years ago along in coastal Alabama. This is land-based resistivity. So this is a snapshot taken by cable that was deployed perpendicular to Lake Shelby. Lake Shelby used to be a lagoon, coastal lagoon, which was connected to the Gulf of Mexico. And eventually this channels or this connection was terminated. And now we have this fresh, and I wouldn't say completely fresh lake, but disconnected from the Gulf of Mexico. In some independent research which we did, we've noticed that when we do water profiles, we see colder and saline water at the bottom of Lake Shelby. And so we decided to take resistivity measurements here. So Lake Shelby is this blue part, top part of the diagram you see. And so what you see underneath is a transition zone. This is the land side. So this is that part here. And this is the side that is here. So towards the Gulf of Mexico. And so you can see that even though the Lake Shelby is disconnected from the Gulf of Mexico, there is connection underground with the Gulf. And it shows us this transitional zone between saltier water intruding underneath the lake and fresh water coming from land. So those are conduits that continue to serve as mediators in this groundwater surface water interaction. Okay, so if we're talking about the aquifer system down at the coast, this is a diagram that potentially has been updated, but originally it was built by one of my first master's degree student, John Ellis, who is now a researcher at the USGS office in Texas. And typically formally we identify 3 different aquifer systems down with the very shallow aquifer which we call A1, 2 to 15 meters. And probably Greg will comment on this. But A2 is between 22 and 80 meters, and everything below that is A3, which is the very deep aquifer. Based on data from trace metals and also radon measurements, we have found that A1 and A2 are connected. So we can prove that there is exchange between the unconfined and confined aquifer there. And that actually led to some saltwater intrusion work we did with my other student who graduated in 2015, where we tried to model this exchange, subsurface exchange. We used previously developed saltwater intrusion model in our department and tried to calibrate it with the electrical resistivity measurements that I showed you earlier. So in this study, we did not find significant saltwater intrusion, which is good news. And now I'm working on updating this model with Dr. Zhang in our department, so more information will come from that. Okay, so I sort of think I covered what are the pathways and mechanisms and whatnot and what drives this HGD. Now I'm going to focus on this how much. How do we evaluate this? It's very difficult. It's not a river that we can put a gauge and we can measure the discharge. And also, it's in the subsurface, right? But also, it's not very high flux. It is low flux, which is diffusive, and it's distributed over larger areas in most of the time. It varies through time, not only seasonally, but also 24 hours, right, with a tide cycle. So what we need to do is to make a lot of measurements over larger areas for extended periods of time, which is difficult. So one way to do it, and I'm very surprised I came to the Department of Geology, nobody had heard about seepage meters, which is the very easy way to measure groundwater seepage, and everybody who has $150 in their pocket, they can do it. So basically you have these drums that, stainless steel drums that we cut in two and get two chambers from one drum. And those drums have an opening and on top. You can put a valve and attach plastic bag to this valve. And then you can stick the drum in the sediment, submerged, so this is underwater. And when we have SGD, water will fill the chamber and replace the trapped water, and it will fill the plastic bag. So if we time when we put the chamber and we measure the volume displaced from the chamber through groundwater, we can calculate discharge. It's very, very simple. So the not that convenient part of this is those chambers are estimating very spotty discharge, meaning that, as I said, this discharge varies through time, through space. We might be on a location or a spot that there is a spring, and then if we want to, and everybody wants to estimate over larger areas, then we will be overestimating this discharge. And the opposite, if we are at a location that we have some clays and there is no discharge, then we'll say there is no discharge, whereas we couldn't capture it. The other thing is we're always looking for undergraduate students doing replacing plastic bags. All right, so there's more elegant method. We have done the seepage meters for the sake of it, but we can do this smarter. And we can do it with radioisotopes. And there are two schools of thought in the radio tracer approach. One is using, large group of people are using radium isotopes, specifically radium-226. And I belong to the Radon Society, obviously, and we're using radon. So these two papers were published in the memorable 1996, which I just found one of my students' birth year. So based on this, which makes us feel very, very old, but based on these two independent papers that were published from different research groups using different isotopes, they found that this is a significant discharge we should start caring about. And they compare it to the river discharge in the nearby areas. And Billy Moore in South Carolina found that those fluxes are about 40% of the river discharge. Something, imagine they're bringing so much nutrients and all that. And Bill Burnett in Florida also found this is a significant flow. Okay. So I said this started as coastal research, but it had expanded exponentially through different environments. And again, from the paper we just published, we did just simple Google search and found and built the statistics. So people were using it for lakes, rivers, estuaries, coastal ocean. And you can see how smart they became very quickly instead of deploying seepage meters. So most of the studies that we found are in coastal areas, but surprising for me because I never actually used radon as a tracer. They use it very actively for evaluating discharge in rivers, groundwater contribution to rivers. Okay. And this is a map of the global distribution of these studies, showing you where around the world people are using this method. And so the different symbols are associated with different environments, and the size of the symbol shows how many of those studies in these areas. And you can see that it's still people who develop these methods are in North America. Most of those studies are here, but they are spreading in Europe and Southeast Asia, but we're still lacking data in Africa, We are lacking data on the west coast of South America, and that's kind of important. This is active continental margin, and I will tell you something about that. But we have done groundwater discharge studies in the Arctic using radon isotopes we evaluated. And that's kind of important to mention because in these frozen environments, we lack severely hydrological data. We assume there is no aquifers there. So the only method that we can use to evaluate discharge is through using radioisotopes. Okay, so why I am advertising the radon so much? Because if you compare the ratio of this tracer in groundwater compared to surface water, you will see this is the best tracer. So when you pick up a tracer, that's what I teach in my classes, you want to have very large difference of the specific tracer or substance between surface water and groundwater, so that if you have seepage in surface water, it will be easily identifiable. So you can see here a comparison between radon, methane, the bunch of radium isotopes as well as stable isotopes, and you can see that this ratio is the highest for radon. Radon is 2 to 4 orders higher in groundwater compared to surface water. Okay, and this is both for marine and saline environment, a marine environment. The other super important advantage is chemically and biologically inert. Unlike radium, which we assume is conservative, the concentrations of radium in water depends on salinity. So typically radium is attached to the rock, so it has to have the contact with salt water in order to desorb for us to see this signal, which makes it not exactly conservative. Okay, it's very easy to measure. Actually, you can collect continuous data every 5 minutes if you put your portable instrument in near surface waters. Okay, so there are some disadvantages. The big disadvantage is a gas. So once discharged into surface water, based on temperature solubility of this gas, you will lose some of it. So you need to evaluate this. Okay, and so if you put your system that we have in our lab, it's not super expensive. Actually, one of those units is now up to 7,000, but it's a portable instrument. You can use it both in the lab and deploy it. It will collect some similar data like the one that I'm showing here. And the blue line there shows the tidal variation in coastal side in Florida, whereas the dots are showing those fluxes of groundwater represented as the signal of radon in surface water. And you guys immediately can identify the tidal pumping pattern. Low tide, high radon, high tide, low radon. Okay, so what is this magical instrument? It fits in a box like this. This is nearshore deployment. Actually, it's a lakeside. I did it in Florida. And it's powered by 12-volt battery. And you can also deploy this if you anchor a boat further offshore. But you can also put it on a boat, and you can run it as the boat drives along the coastline and collect this data. I did this deployment offshore in Florida, monitoring some submarine springs there. And thankful for me, there was a platform built offshore by USGS. They were monitoring already the springs, salinity, and they had some other devices. And I would go once a month and deploy my system and would collect radon data. So you can become really creative with this instrument. So the magical instrument is this box here. These are 2 batteries that we usually connect to power for. They would last for about a week or so. So based on these deployments, actually I want to show you my favorite set of data that I collected at the spring site in Florida, because it demonstrates several driving forces in this area. So this is from this USGS stationary that I deployed my instrument, and it was sometime in February. And what you see here, the blue line is the tide cycle. Also, the dashed green line shows you salinity. So you would see variations of salinity with the tide as well. So we were seeing some fresh discharge. And simultaneously, we were measuring radon, which is this signal here. And from the top, you see we had a significant rain event, which passed through the areas, a storm. And you can see that right after the storm, the system, it's a karst system, so the flow through it is very fast. And you can see immediately how salinity dropped from 27 down to 3 ppt. And if you look at the radon signal, which is on this axis, it was relatively, for normal natural levels, went all the way up to 7,000. But at the same time, continue this tidal pumping cycle. So you see the response from the storm as well as the tidal variations. Okay, so what do we do with this radon data? So we obviously take these time series measurements in water, and we build a mass balance model. What does it mean? We just start figuring out, so we measure total radon in the water, and we try to understand sources of radon to the water and eventually sinks. And this is what this diagram shows. So again, published in our recent paper. By the way, we work through all environments, both marine and fresh environments, and we share free codes in R and MATLAB. So one can just go collect data with the instrument, plugging into these models and calculate discharge. So typically for the radon inventory in the water column, the sources are from diffusion from the sediments, because the water is in contact with the bottom. So some of radon would be produced from decaying radium from the sediments, so we need to account for that. If there are influxes from streams, then we have to account for that, because some of the streams are groundwater fed, and they will bring some radon which is not delivered through groundwater discharge. We also have to account for the tidal variations. And the inventories here is our activity per square meter for that reason. And then we will lose some radon from atmospheric evasion, or if we have outflows from the area. And from this mass balance, the only one remains the contribution from groundwater. And then we take this flux of radon to the system and divide it by the groundwater end member, and we calculate seepage rates. As simple as that. So we have compared, usually when I talk about this, actually the first time I presented in the UA, somebody said, what is this magic? Give me seepage meters. This has been done many times. And this is an example from this very first study when the definition of SGD was placed. And it shows comparison between radon model on the top diagram and electrical continuous seepage meters. I did not mention that there are such devices, seepage meters, that are not manual. They work on different principle, but it was producing continuous data, and they were comparable to what the radon model would give you. So, and they actually had, this was a working group, and they compare modeling as well. They have a special issue in biogeochemistry from that time, so if somebody is interested, I can share this information. So, most importantly, okay, now we know, we convince people this thing exists, and we try to figure out, compile the data and see where it's been measured, how much it is. And this is, there are two papers I recommend looking at this. One is by Audrey Sawyer in Nature that came into 2016. And she sort of did back of the envelope calculations to figure out which area, global areas would, in which areas we would have preferential HGD. And she actually concluded that active continental margins should deliver more HGD compared to passive, and there are different mechanisms into these two different types of environments. But bottom line is what you can see is here that we have enough data now for different environments, and we have pretty good understanding of this phenomenon. Okay, to bring us back to something we care about, is going to continue with showing you some data from Mobile Bay, the work we did in the last few years. And in this work, we compare, this is the first work done to evaluate HGD in Mobile Bay. So the first thing what we did is to look at the development of the area and then figure out how this would impact the quality of discharge. So in our case, we put 3 time series stations that we monitor HGD at least twice a year during dry and wet season. And those are the ones that are noted with star signs. And this is what we have seen in Mobile Bay. So the map on the A map shows you radon anomalies. And in this case, we took an average of the radon concentration in the whole bay. And then the areas where we see higher than average would be these red areas of positive anomalies. That would show us preferential pathways of HGD. And you can see that most of it is happening on the shore of Mobile Bay. This is what radon gave us. Using the resistivity meter, the cable that we drag behind the boat, we get this picture. And can somebody spot what is the difference? Besides that, these areas coincide very nicely. So if you look at the mouth of the river, we see the fresh signal very nicely with the resistivity cable. But the radon doesn't detect it because this is fresh water that is not coming from groundwater. So that's the beauty of radon, that it will tell you not only the composition, is it fresh or not, but it will tell you if it's coming from groundwater or not. So the resistivity can tell you fresh or saline, but the radon will tell you exactly it's from groundwater, which is very difficult to distinct these two sources in estuaries like this, because most of the water is coming from the river. So we want to know, just to single out the groundwater contribution. So looking at the mechanisms, we did find tidal pumping being one of the mechanisms. We did see storm forcing. So this is published data. I'm just going to go quickly through that. And the big question is, why should we care? Okay, we determine where it is, so why should we care about that? Well, we do care specifically in Mobile Bay because we do have those, if I can go back to my mouse, I play the video. Oops. Nope. Well, this is a video showing you a Jubilee event. It's basically fish that is swimming to shallow waters near shore and gasping for oxygen, because we have these regular anoxic events in Mobile Bay where the oxygen level dropped to hypoxic levels, and this is what the fish does. It's killing the fish, but people, especially at the beginning of these events, are very happy because they can go and grab fish. They can fish with the bucket. So that's why they call them the Jubilee events. But we are concerned about this, so we try to understand what is the reason for that. And earlier work by a colleague of mine, Jeff Tick, which you most likely know, and his students showed that there is high nitrate in the coastal aquifer in Alabama. And so bingo, I came as a brand new faculty here. So it's like, that's what drives the low oxygen. We have eutrophication, and this is consuming the oxygen, and nitrate is driving all that. But is that the case? Well, here I'm comparing the groundwater data that I showed you, the distribution. We also measured regularly dissolved oxygen, and you can see that in the areas where we have HGD, we also have very low oxygen. So that's sort of not good news, but sort of confirms that must be coming from groundwater. And actually, if you pull out this map from Wikipedia, which we don't know the source of, but it shows that most of the gibberellins actually occur on the east shore of Mobile Bay. So again, success, SGD drives the gibberellins. Okay, so then we looked at what exactly SGD brings, and we found that during the wet season, this is comparing river sources, nitrogen sources versus SGD. You can see the river is outcompeting SGD, no question about it. But when we look at the dry season, when the river is low, SGD becomes important and actually delivers 25% of the total nitrogen to this. And specifically, almost 90% of it goes on the East Coast. Okay, so we did a sort of nutrient mass balance where we had data for 3 years, dry and wet seasons, on the east shore and west shore from this time series that I just talked about. And we had data from a well, which is our favorite agricultural well. We go and measure a very high nitrate in there. We also deployed piezometers. Those 1, 2, 3, 5 tubes that you see are piezometers we drill perpendicular to the shore. We sample those, and this is what the balance shows. So in terms of nitrate on the east shore, we have high nitrate, both during dry and more during wet for sure. And this is in the farm, on the well that is inland. But when you get to the piezometers, suddenly we see very low nitrate. So almost just kind of surprising. And when we do the mass balance for nitrate, we actually have deficiency during the dry season and the wet season. So where is the nitrate going? But when you look at ammonium and DON, which are the reduced forms of nitrogen, it's exactly the opposite. Huge surplus of ammonium and nitrogen and DON, and some enhancement of PO4. Okay, so similar thing on the west shore, but not as dramatic in terms of those reduced fluxes as in the east shore. So it turns out that the nitrogen on the east shore is not nitrogen from agricultural areas. It is reduced form of nitrogen, and we need to figure out where it's coming from. Okay, so our conclusion is that most of the HGD fluxes are reduced nitrogen, and that the sediments, as the water travels, are sink for nitrate. So we did something that everybody does to figure out nitrate sources, stabilized N15 and O18. This is all the data from Mobile Bay rivers, groundwater. We had tons and tons of data, and that plot that sort of identifies where the nitrate is coming from. And most of 50% of our data falls into the category it's coming from the soils. It's not coming from agriculture, it's coming from the soils. So then we start digging the ground there. Sorry, but we had to get to the bottom of this. So these are snapshots of electrical resistivity in the area. So the red plume here is your freshwater SGD. So again, low tide, you see larger plume. High tide is shrinked because of the tidal pumping. But most importantly, we use this data so that we can drill those piezometers and probe this plume so that we have a representative of what exactly is going into the bay. And our mass balance is based on that data. So we have sediment cores, and we start looking at those cores. And I want to point your attention to the specific core, which is in the southeast part of the bay. And we identify large organic layer in this area, which is this black B layer here. And we found that SGD is flowing through this specific layer. So it must have some impact. So we wanted to see whether my original idea was this is old deposit that most likely through sea level change and all that jazz that I was talking to you about. But this is very surface layer. If you can see, this is data showing, we dated it using lead-210 techniques. So the highlighted area here is the layer. And it was deposited in 1967 around cesium peak. You guys know a little bit more about dating. Okay, and the other thing we found that just above this organic rich layer, there was this huge, we would calculate huge sedimentation rates, which is not normal. This is artificial. So hence I have taken the data from there. But in the 60s and 70s, something happened to the system that basically built this sort of stratigraphy. So what we are suggesting here, after talking to local people, is that land development of the area had impacted the marsh system in the area. So what they actually did is this used to be marsh system that was leveled, covered with sand, and this layer is now further down. It becomes decomposing, and the shallow seepage goes through there and brings us all the reduced nitrogen, which we probably would have figured out without the sophisticated isotopes that just go and talk to local people. Okay, so that was confirmed also from C13 and C2N ratios. This is another cross plot people use to figure out what kind of vegetation is decomposing. So the full dots is our data. It shows vascular plants. So this is the old marsh, not that old, but the one that in 70s was covered. And this was also confirmed from DOM analysis, this organic. So in conclusions, the seepage in Mobile Bay is very heterogeneous, so preferably pathways on the east shore. The inland sediments are sink for nitrogen. We did not see anthropogenic nitrogen going to the bay. We saw DON and ammonium, which are the products of decomposition of organic matter. And this is a result of modern development of the area. That's our conclusion. But these kind of locations exist in other parts, not only in Mobile Bay, and must be examined, and we have to figure out what is going on. It's very easy, and I'm totally for claiming anthropogenic impacts, but it turns out in that case it wasn't. And this has been seen everywhere, because we published recently this paper which shows on global scale in muddy coast, groundwater delivers mostly reduced form of nitrogen, DON and ammonium. This is compilation of many, many sites. So we need to look at those and figure them out before we point who is responsible. And finally, I want to leave you with this slide showing in the same paper, we looked at the biological response to HGD. These are 3 different scales, and what you see is either increasing, for example, organism abundance, or decreasing. These are the number of studies that we found, whether it's increasing or doesn't have any effect on that. And this is another field that we should fill gaps and understand how exactly HGD is impacting. And with that, I'm going to stop here and ask for your opinions and questions. Thank you.